Okay, so 10 to the minus 5 coulombs is going to be a large charge. You would see significant sparks in lab if you manage to get that much charge on something. We want to find out if that, and we know that the materials are filled with protons, electrons. We want to find out if that 10 to the minus 5 microcoulombs uses most of the protons or just a few protons in the material. So I brought with me, it's a bag, this is all dirty. In here is a genuine charcoal briquette. It's mostly carbon. I'm going to guess it's 2 ounces of carbon, although I'm betting that's high. And I'm going to find out the total charge. So this is our first example. So EX is for example. We want to find out first, what is the total charge of the protons in 2 ounces and 2 ounces is 57 grams, is Wolfram alpha of carbon. And that would be the net charge of the charcoal briquette if somehow the electrons had vanished. Then we're going to try to figure out if the electrons vanished. Which they can't, thank God, because we're going to find out this blows up big time. And because charge is conserved. If the electrons vanished, how much energy would be released? And there's going to be a lot of energy. This energy would be released as an explosion. So we're really calculating the explosive energy of this charcoal briquette if the electrons vanish somehow. Okay, so to address the first question, we need to know something about how many atoms of carbon are in 57 grams. So we're going to have to figure out the periodic table. So, unfortunately, there's no periodic table in this classroom, but you guys can all look them up online. You've all seen them, so this is the periodic table. There's some number at the top, an integer. And that thing is called the atomic number. So we're interested in carbon. So the atomic number of carbon is 6. There's a symbol for the element inside, in the middle. This is carbon. The symbol for carbon is C. And there's a decimal number at the bottom, that's the atomic mass. The atomic mass of carbon is 12.01. And those two numbers will allow us to figure out how many protons are in 2 ounces of carbon. So, step out of the frame for a second. All right, so first we need to use the atomic mass to get the number of moles. So we need to know what atomic mass is. Atomic mass is just the number of moles. I'm going to mess this up, aren't I? Is the mass grams of 1 mole of material. So we're We're eventually going to need to know what a mole is, but this will get us a little closer. So we're going to calculate the moles. We'll use little n for this as the symbol for moles. And the moles of carbon is just going to be the ounces of carbon over the atomic mass. And that will give us 4.7 moles of carbon. Okay, well that doesn't really get us all that much closer. Now we need to know what a mole is. All right, a mole is just a number of something. So it's one Avogadro's number. So it's one Avogadro's number of something, and Avogadro's number is 6.022 times 10 to the 23 somethings. Okay, so we know the number of moles. We have 4.7 moles. We know what Avogadro's number is. We can compute the number of atoms. And I'll just let capital N be the number of atoms. So to get the number of atoms, we take the number of moles and multiply it by Avogadro's number. And I promise the calculations will get hard in this class. So we have the number of moles times number of atoms. 4.7 moles, 6.022 times 10 to the 23 is Avogadro's number, which gives us a relatively gaudy number of atoms as 2.8 times 10 to the 24 atoms of carbon. Okay, so each atom has some number of protons. So we're getting closer. So that's the other thing we get out of the periodic table. The atomic number will give us the number of protons. We'll use capital Z for the atomic number, and this is just the number of protons in an atom of the element. So, for carbon, Z is 6. That means that every atom of carbon has to have 6 protons. If you have different than 6 protons, you're not carbon. So with this, we can compute the number of protons in microcud. We'll use n underscore p for the number of protons, and it's just the atomic number times the number of atoms, which is 6 times 2.8 times 10 to the 24 is 1.7 times 10 to the 25 protons. getting closer, we wanted the charge of those protons. Each proton has exactly, not sort of, not close to, but exactly the charge E, the fundamental quantum of charge. So the charge of the protons is the number of protons times E, 1.7 times 10 to the 25th. E is 1.602 times 10 to the minus 19, so it's small, but we got a lot of protons. That gives us a total charge of protons in that charcoal briquette of 3 million coulombs. So a giant charge for us in lab is going to be 10 microcoulombs. So there's 3 million available coulombs in this small piece of carbon. So when we make net charges in lab, we're really removing, it's always electrons we move, we're either removing or adding a tiny number of the available electrons. So we're looking at a process in lab where we're making small changes over this giant sea of charge. Okay, my second question was, okay, we've got this chunk of carbon. All of a sudden, for some reason, the laws of physics change and electrons vanish. I want to know the total energy that it would blow up with. I'm going to approximate it as a 1 centimeter sphere, because physicists can't do that. So I'd like the total charge of a 1 centimeter sphere containing a net charge of 3 million coulombs. Well, this is going to take us a while. So this is something we'll finally understand in week 6, but I'm just going to report the result for you. In week 6, we'll be dealing with the capacitance. You'll find the energy of a system with capacitance is 1/2 the charge squared over capacitance. And you'll also find the capacitance of a sphere. 4 pi epsilon naught r. Epsilon naught is a fundamental constant that controls the strength of the electric force. It's 8.85 times 10 to the minus 12, so it's quite small. So if you plug in the numbers there, you get the total energy of that charcoal briquette as 3 times 10 to the 24th joules. Now the total gravitational energy here wouldn't light a match. So the total electrical energy that is stored in the fields, if the electrons vanish, is enormous. And if you convert that into megatons, you'll find that it would explode with an explosive energy of 800 million megatons. For reference, the US arsenal approximately 10,000 megatons. So this thing would explode with energy many times greater than the entire US nuclear arsenal. So the electric force is quite strong.